Welcome everyone. Now we have came to the end of our P103 lecture as well. Now this is the end of the basics that we have discussed all together. Right? We have came to the end of the module of units and dimensions. Now we are entering into the domain of core physics. Okay. So before that, I want you to appreciate a small thing that we use daily. Okay, we use this in our everyday calculations. In physics problems, we use it long period of time and in larger number of times. So this thing is called a Fermi approximation or Fermi problems. You use Fermi problems, which is basically a back envelope uh, kind of solving method. You use an envelope and you use an easy way to estimate in the back. Okay, that's how a back end of the envelope kind of problem. You use approximations to carry out some easy calculation. So like for an example, you use it basically in the case of acceleration due to gravity, which is 9.8. So you approximate it to 10. So with that approximation, you can see that the percentage of uncertainty within this value is less than 2%. It is 2%. So you can go as far as 9.51 and still approximate this value to be equal to 10. So that's well within 5% error. So this is kind of a limiting factor that you use daily in your calculations. Now this is a bizarre thing. Okay, I want you to be convinced that this is a bizarre factor that you use daily. So for that, I'm going to introduce some basic examples. Okay, using those examples, I can convince you that this is bizarre and this is something that you need to appreciate before using. So first thing is that if you have a jar of coins, you say it's 5 kilograms, right? So if it is you have coins inside the jar and its weight is 5 kilograms, and you can see that uh, the number of coins, if one coin is equal to 5 grams, right? 5 grams, then you have 1,000 rupees or $1,000 or 1,000 pennies inside that jar. Okay, so you know that for a fact from estimation itself. Now if you find out that when you calculate, you find out that there is 5,002 grams, then each coin is almost 5 grams. So this 2 gram doesn't account for anything. Still you approximate it to be equal to what? 5 kilogram, which is 1,000 rupees, right? You can go 4,998 as well. Okay, still it is well within your uncertainty. This is something that you daily see. Now if you take a 1 kilometer length and you line up them with pennies, like coins, and each coin is approximately 2 what centimeter 2 centimeter long, and you need to fill out 1 kilometer, you need around say 50,000 coins. You can do the calculation yourself. So 50,000 coins you need, that is 5 times 10 to the power 4, right? So you can say that the 1 percentage of that is 5 times 10 to the power 2. Oh, right? So the 1 percentage of 5 times 10 to the power 4 is 5 times 10 to the power 2. That's a big number. That's 500, right? So even 500 is okay for you. Okay, now let's come to a different path. I'll do something different. Now if you want to estimate the mass of water on the earth's surface, right? Mass of the water on the earth's surface, if you consider this is earth, it's almost spherical, let's say almost spherical, and you need to find out the amount of water present on the surface, right? On the surface you can find out the amount of water. There are hills and all that. Now you know for a fact that radius of earth, right? Radius of earth is equal to 6.4 times 10 to the power 3 kilometers, right? That's a fact. Now if you have, then you can find out the mass of water, right? Mass of water will be equal to density times the volume, right? But only 75 percentage of earth is covered with water. That means times 7.5 by 10, right? Only 75 percentage will be of this mass will be that of water. And if that's the case, then we can substitute for the values. For the density of water is 1000 gram per meter cube. That's the density of water. And you have, like, volume will be 4 times the volume of a sphere will be 4 pi r square, times the distance. This is the area and this is the distance. That means the area covered by the surface, this is the areas covered by the surface plus the distance upwards, right? That makes you, that's completely fill the water inside. That's the volume of water. Okay, area times distance is also a volume. Now if that's the case, you can substitute those values and you get 4 pi times 6.4 times 10 to the 6.4 times 10 to the power 3, the whole times 10 to the power 6, because it's in kilometers and we have to convert it in meters, the whole square times distance average height of water. It can go up to 10 kilometers depth, and the average will be around 1 kilometer. Okay, so you got that. And when you substitute that value into here, times volume times 0.75, and you will get, you can calculate that yourself, you get 3 times 10 to the power 20. Okay, that's a big value. That's the kilogram of water. That's the gram of water present on the surface of earth. Now if you commonly do something, that you commonly do is approximate it into 10 to the power 20. Now this is something that you do all the time. Now I want you to see the difference between this and that. This 2 is 2 times 10 to the power 20. That's bigger than our value itself. So that means this kind of approximation, if it is within say 1% or 5%, it's okay. So this is what you do in daily life, and I want you to be seriously reconsidering the importance of limiting our approximations and using this concept in our daily life and how useful it is. Okay, we don't need to pick out all the big values. Even something as huge as this can be eliminated, and you get to approximate things as 10 to the power 20 grams. That's very useful. Okay, with that I'm ending. This was very simple. I know this is very easy, and I don't want you to be worried about anything. This is very simple, and I'm ending this module with here. Okay, I hope it's a nice and easy end. Okay, thank you.